Ooh, say my name, say my name. You know what's it about you? Let's refresh my stream. Manager. It's sending me live. Yo, what's good? We're tuning in, coming at you live from the northern beaches. You know what happens? Every time I go live, it seems my computer goes a bit laggy for a little bit. But let's do what we always do because we haven't set up a...
Sorry, I don't know that.
Man. Let's do what we always do because I haven't yet set up a Discord integration or a Twitter integration for letting people know that I'm live. See, look at this. We got Lag City. My RAM starts to get taken up. Okay. I'm going live on Twitch. More time series deep learning with TensorFlow. Let's get a little graph emoji and come and say hi. We'll get a little waver out there. Boom. Twitch TV. And let's get a little bit of Discord action. Apparently Discord have uploaded their logo, updated their logo. We'll bring this one over here though. I'm going to minimize this. I really want to fix up this stream setup so they don't have... I wonder what the optimal window system is, you know? Or is it better just to keep it rough? Yo team, live on Twitch coding with TensorFlow. Come and say hi. Little wave emoji. I better wave first, you know. Hey, why didn't this turn into a link? We need the HTTPS, don't we? HTTPS, boom boom. Wonderful. Yuchi, what's good? Pseudo Maze, how are you? HY96B, hello. And Agus, hey, what's going on? Happy Sunday indeed, Ashik. Let's put the final nail in this model, hey? I've got an idea of where we're going to go. Because it's about time we got rid of what we're doing today. We already went through that yesterday. So now we are up to the official next. I'm going to get rid of this. Here we go. See if we can loop the functional API to create real stacks. It is Sunday here, so this is a Sunday stream of greatness. Now, I did pull a muscle at Jiu-Jitsu during the week. I was supposed to be at a BJJ, Brazilian Jiu-Jitsu competition today, but I hurt a muscle in my stomach, so I've pulled out injured. Now, also sitting for long periods of time isn't that great for it, so let's... I need to set a timer. In about half an hour, I'm going to stand up. So, hold me to that. And I also have to do some stretches. So maybe we'll only do this, this will be maybe an hour and a half stream or 2 hours or something like that. But yeah, my computer's going quite slow at the moment. But yeah, this is what I want to do. So, last time we got the model built, but I don't think it's the fully N beats model. Shredded AI stuff, yeah, baby. Yeah, it's a Sunday Fun Day stream. By the way, if you have any ideas of what you'd like to see in future streams, please let me know. We'll just run this for a little bit. We're working on a deep learning model for univariate time series. Probably in the next stream, after we get this model really down pat working for a univariate time series, we will start to use it for a multivariate time series, and then we will build in some uncertainty through a couple of methods I'd like to try. I think, to me, it makes sense that you could create uncertainty through ensembling different models with different loss functions. And what I mean by that is if you train a model with, say, 3 different loss functions, you could build in prediction intervals based on the variance between the different predictions with different loss functions. So say we built this first model with MAE, which is mean absolute error, and then we built another model with MSE and another model with MAPE. We could combine those 3 models' predictions to both ensemble and then measure the variance across to create a prediction interval, which is important with time series. So if we look at prediction interval time series. Alex, what's good, my friend? Wanted to see how you learn full stack deep learning. Yeah, that's a great idea. We'll get that going in a future stream for sure. Okay, so here's some. Do they have a nice graphic on what prediction intervals look like? Yeah, this is what we want. We want something like this that'll give us a range in where our time series predictions appear. So that'll probably be a future stream. In this stream, we're going to put the nail in the coffin in the NBeats model. We're going to get it finished and built. It's about time we did so. See, the code resources that I found were quite complex. I think I found a simple way to build it just with the functional API. So that's what we got done in the last... This is what we got done in the last stream. So see, our problem is, though, with this, is if I look into downloads, where we have a large version of this. So if we zoom in here, we've got the functional model here, which is a functional block. And then, so the block, I might rename this NBeats block. Then we have a whole bunch of subtract layers here, which if we look at the NBeats architecture, is trying to replicate what's going on here. I've got a song stuck in my head and I really want to play it, but Twitch is probably going to ban me. I've never got that with music. Like if you're just playing music, sure, there's copyright laws and stuff like that, but surely the technology's there to siphon whatever amount of revenue they would have got from me playing that music. Supernova, what's going on, my friend? Yeah, the Udemy course has had a big update in the last week or so. About 10 hours of video got added of the TensorFlow course. This is probably going to be part of Project 3, a simplified version of this paper. Because like to replicate this entire paper would be far too long series of videos, so we'll build a simple version of this model in it, as long as I can get it working here. Come on, man, stop bouncing around. Okay, yeah, so I need multiple of these blocks. So if you see here, block 1, then it has a subtract layer, block 2, block K, etc. This is what I need to replicate. Give me some downloads. Right, so right now I've only got one block here. whereas they have multiple blocks. So see, we have stack input into a block layer. So the main task here is to replicate this block to mimic what's going on here. But if you see, what this little subtract symbol is they're subtracting the backcasts from, this is a skip connection, right? This is residual connections. So this helps the gradients pass through the blocks. So if we have an input, what we're doing is we're passing the output as well as the input to just a subtract layer. Same over here, but it's a addition layer. So this is where our addition layer comes in over here. But let's go back. So what I'm going to try and do is I'll turn this into a layer class. So let's do that. I'm going to put this can be nbeats block. So let's maximize this. Let's put up another cell here. I've already created the nbeats block, but I'm going to create it again anyway, just to keep practicing layer subclassing. Oh, I've got a song stuck in my head, and I just want to keep singing it, but they're not gonna let me, 'cause Twitch have copyright laws. Maybe I could put it in my headphones, then you wouldn't be able to hear it. Create nbeats block. So let's turn this into a subclass of TensorFlow's layer. nbeats block, tf keras layer. This is layers as a plural, and then we need an init. And it's going to take a fair few inputs here. So let's do self input size. What else should it get? Theta size. Horizon. And neurons. And layers. Okay, and then we can go super. Init. Now, how can we do this? So we want input layer equals, we'll turn this into a list, tf keras layers dense, and then we want n neurons. You know what? I'm going to actually create this as an input layer. Actually, how do I want to do this? Now this will do. And neurons. Big Verd, what's going on, my friend? Supernova, yes, feel free to share these projects on wherever you want. However, I'll always going to tell you as well, as much as you learn from the projects that are in the course, always beware that you're going to learn a lot more from applying that knowledge to your own projects. So that's kind of the touching the stove mentality. So the input layer, we need a list of layers, right? Because this is going to be a fully connected stack of layers. And then, we'll do self.input layer, self.hidden equals self.input layer plus, can we do this? Like, is this legal? I need to upgrade my Python OO knowledge. And neurons activation equals ReLU 4 in range and layers -1. Alternatively, we could just code this layer by layer. That might actually be better if we just put it into the call function. Maybe we could do that. What's the best way to define a custom layer? Yeah, so they define it up here. This should be fine for us. And then we want a theta layer. Equals yeah, is that going to work? I'm trying to figure out whether this is this syntactically correct. If I reference self.input layer here, and then in the constructor I also have self.input layer. See, this is where my OOP knowledge falls down. Supernova, I think you can only follow on Twitch. I am eligible for subscribers, but that's paid for on Twitch. I haven't activated that yet. Theta layer, which is a dense layer with a linear activation. Why are you always in a mood? And we'll give this a name of theta. Okay. I think that's all we need. Now we need to do the call. Inputs. So this is going to take an input of horizon, and then we need to pass it through just like this. So x equals inputs, and then for layer in self.hidden. X equals layer x, and then we need theta. Theta equals self.theta layer. We'll pass it x, and then we want to have, it's going to return backcast forwardcast equals theta. Now this is interesting, where we'll just run with this anyway. Input size, and then where would I give this a name? Is it in the init? Name equals and beats block. We'll see what happens here. And then we'll return backcast forwardcast. So this is just a subclass version of this. So we have input, which is the inputs here, which is going to be some time horizon. So if we look at this, we've got a look back period. Yeah, I will activate. Oh, thank you, Supernova. I really appreciate that. I will activate the subscribe button when I, probably after this stream. Adam, hey, what's going on? Oh, thank you, Adam. Don't try to be a hardware store. Try to be an artisan craftsman, which I like. Yeah, I totally agree. Think about all the people you admire, right? They're usually pretty darn good at a certain craft, whatever that craft may be. And the only way to get good at a craft is to have the discipline to continually pursue that craft. So let's see if this block layer works. And so what I think we can do is go block layer equals n beats block, and then we can put in the input size is going to be the input size, the theta size is going to be, these are all hyperparameters that we've set up, and the hyperparameters in this paper, I actually really like how they've done it in, I think it's table 18. Yeah. Table 18 is where all the hyperparameters are, but we'll come back to that later. So let's just code here for a second. We can come back to the paper if we need to. So we'll initialize an nbeats block as a layer just to make sure we've got what we need. And right now our code is extremely messy, but that is fine. We will clean them up. We'll clean it up later. Is this going to work? Yeah, we need horizon, don't we? So the input size is the look back period, and the horizon is how far we want to predict in the future. So of course these are arbitrary values, but it's going to depend on what you set your data up to be. So I'll just show you. We've seen this a couple of times in a previous stream, but just if you're not sure. So with the time series problem, you can convert it into a supervised learning problem by you use the past to predict the future. So the input size is our look back period, which is here. The theta size is this here, theta. Horizon is how far we're trying to predict into the future. Number of neurons is how many neurons we want in each layer. And number of layers is, because this is a fully connected stack of just 4 layers, we've got a list here, a list comprehension, which is creating a list of layers. The only one that's different is the input layer, where we've defined the input shape. And the input shape is input size, which is again the look back period, which will just be a long vector of time steps. So let's see what happens if this code is actually working. What have we got? We've got something wrong here. Input shape. Int is not iterable. Yeah, we had this last time. We had an issue with the input size here. But when we create it as an input layer, it seems to work. Let's go to oh, Big Verd, you're on TensorFlow Quantum. That's amazing. To be honest, I know almost zero about quantum except for like the high level theory stuff that you see in Quantum 101, where it can be multiple states at the same time. And yes, I have seen the new Deep Learning AI ML Ops course. It looks really great. However, as I said, I think I'm done with courses for the time being. I need to, after I finish building this course, I need to get some skin back in the game and build my own projects. All right, so the input shape is really pissing me off for this layer. I'm not sure what is going on. Yeah, so it takes an input shape, an ND tensor with the most common input shape would be 2D input shape. So can I just have you know what I'm going to do? I'm going to just create an input layer here. Will this work? What if I can this, and then the input layer here is just tf keras layers dot input, and then the shape is the input size, and then it can just do its thing and figure it out. What happens if we do this? Wow, that worked much better. So now let's see what our block layer does. We've got an nbeats block here. Is this going to tell us a D type? Float 32, but is this a TensorFlow layer? Maybe we have to build it first. Yeah, Alex, yeah, you're totally right. That Steve Jobs video, that's something I've been thinking for a while now. Okay, so let's create some example inputs. So block inputs equals tf ones Is this going to work? Kera's tensor object is not callable. That should be fine. Maybe we've got something busted here. What if I just can this and can this? I'm trying to make this as simple as possible. Okay, there we go. So that seems to have worked. So now we can create a block layer by using this. I wonder if we can substitute this into this stack layer here. So the block would replace this. So they do this in the TensorFlow guide with sampling. I wonder if we can create this here. So this is going to return our block outputs, which is what we want, and the same thing for this is the backcast, and this is the forecast. I'm just going to bring this up. Write some very hacky code here. Beautiful. Now let's have a look at our stack model. Oh, yes, team. We might be on here. We should have 30 blocks. Oh, this might look amazing. What do we want to do? Import plot model. Oh my gosh. Plot model. This might take a while. Oh, yes. This is what we're after. Have a look at this. I need a name for it. I'm going to name this. Name equals. Oh, wow. That timer went off very quickly. What did I say I was going to do? I'm going to stand up after the timer. Mbeats block. I think I may have just built a very simple version of this model. Let's stand up. Do a little stretch. Dancing. So I hurt my psoas muscle. I'll show you it. Psoas muscle. So this one will bust you up. Oh. How is this one $119 and this is $20? That looks actually amazing. I might actually buy one of those after this stream. But so this is a psoas muscle, connects your spine to your femurs. And so when I was trying to bend like this, it really hurt. So this muscle, if you imagine, just sucked in. And so I was stuck like this, but couldn't bend over because it was so seized up. So I've been doing a lot of hip release stretches and a lot of... what I basically have to do is, because I spend a lot of time sitting, this muscle gets really tight. And so I've done a lot of release type movements to untighten it. But let's... Alright, so I've got some exciting progress here. Let's really name this. So we've got a... What have we got wrong here? We've got a beautiful looking model here with a lot of skip connections. So let's have a look at this. So if you see, we have a block. Oh, what is the functional block here? Ah, we're still using the initial block here. But that's okay. We'll fix that in a second. But what's happening is this is our skip connections. So if we compare this to the paper, we'll find figure 1. Human anatomy team. You get everything in these streams. Okay. So, we pass it to a block, and then we skip connect the outputs. So, have a look at this. This is marvelous. Let's line these up. So, remember within each of the block, there's this stack here. And the block outputs the backcast and the forecast. But if we have a look at this stack, the backcast, which is this left arrow here, gets subtracted with the previous layer's backcast. And then the forecast gets added, and then we pass the forecast to the next block, to the next block, to the next block, to the next block, and so on and so on. And so we've got this little subtract section here, and we've got this little add up section here, which just continually adds it. See how we've got the global forecast here? Just continually adds it until we get to the output. Right down here. Right at the end. So see how we've got a big add right at the end? That's what we've built here. And we've just stacked up these blocks, something fierce. Now, why do we... Oh, we have 59 because we've run this cell more than once. That's okay. But yeah, this is our skip connections here. Subtract. See this? And then we subtract it and feed it into block 2. But we add the forecast. Okay, we've got some great progress here. Now we need to fix this little input here. We need to fix the original residuals and So what we might do is, I don't really want to repeat the creation of this, but I like the fact that this has a name parameter here. Samantha, what's going on, my friend? Welcome to the stream. I could set these all to defaults, right? Because I don't really want to recreate this. We'll come back and clean this up in a second. Let's just... fit it and make sure it works. Didn't I just do Horizon? Repeating myself here. So we're going to have one more block. I wonder if I can get away with this not being here. Yeah, don't worry. Don't focus on how much you learn in a day. Or so Samantha says he went through 2 weeks of ML by Andrew Ong yesterday. Yeah. When learning, I forget like 99% of what I learn. So day to day, it might not feel like you learn much, but week on week, you'll certainly know a lot more, not week on week even, month on month, 6 month on 6 month, you'll certainly know a lot more. Okay, so has this got, where's the initial block? Okay, so it's not giving it a new name here. I wonder if I don't pass this as name, if I just set this to keyword args. All the real benefits in learning and anything comes from long term. Okay, here we go. So we have an initial block. Okay, this is beautiful. But we're doing a lot of repeating code here. I'd like to do away with this initial block, but I want to see if this model will fit. Supernova, how do I deal with the data that has spaces in column names and pandas? Yeah, I'm the same as you. I just rename the columns to be more flexible. So now we should have a training data set. And we should be able to get a summary of our model. Beautiful. So we have a fairly big model here. Do we have a GPU? I believe we do. We have a Tesla T4. Let's fit our model, hey? Equals stack model.fit train data set. Let's see what errors we run into here. Of course we need to compile it. See, I also like this is that we have optimizer. They use Atom Optimizer with the default settings. I wonder how much we could speed up. Let's have a look at how long this takes to fit. Let's see if we can input mixed precision training. Oh, boom, look at this. Our model is fitting. Easy money, baby. We got that fit. That's what's up. Okay. So look at that. That's very exciting. We got the NBeats model working. So that took us a fair few streams, but I'm pretty sure we've got the architecture down pat. You can check this and tell me if it is or it isn't, but I'm pretty sure this is our architecture. Look at this. Beautiful skip connections. We find figure 1. Come on. Show me figure 1. All right. So we create a block, fully connected layer. We have 2 outputs from a block. We have on the left, we have the backcast, and on the right, we have the forecast. And then if we have a look at the stack level, we have a subtract layer on the backcast, right? And then we have an addition on the forecast. So boom, look at that. Is it possible to learn ML and DL in 1 month to get a job in DL? What quick method would you suggest? I suggest no quick method. Don't rush these things. Learning anything worthwhile takes time. The only quick method is to develop a discipline to continually keep learning. So if you want my best advice on getting a job, look up Daniel Burke. Start the job before you have it. Yeah, there we go. Read this post. These are my videos that will help you for that. And my blog posts that will help you for that. But we're back to coding here. This is actually so exciting. I'm so happy that we got this finished, done. So let's actually train it for a decent amount of epochs. Our data set is fairly small too. So let's see what happens when we fit it on 20 epochs. Are we doing any better than our dense model? Yes, a sick mullet will help you get a job. So we're getting wildly fluctuating results. Cletus says, yeah, is a sick mullet required? Yeah, if you have a sick mullet, people will know that you mean business. They're like, this guy, like, even forgot to get a haircut of half his head. So he must be spending all his time improving his skills. So it's like, he's so time poor, can't even get a haircut. That time must be going into getting better at something. So, look how fluctuating our results are. Like, the MAE just bounces around something fierce. What if we trained for 200 epochs? Wow, Ashik, that's amazing. Blogging consistent 170 days, podcast 15 days. That's terrific. Keep it up, my friend. It's all practice. Yeah, so the MAE gets... We find that it doesn't... Remember, our training data set is fairly small as well. Okay, so we're starting to... Our model starts to converge. Oh, it looks like it's starting to converge down here. This is good. Like it's sticking it out. At about 44 MAE. Oh, looks like we're consistently getting down. So we just have to wait for our model to converge. Let's start plotting the history, hey? TensorFlow deep learning. Okay, I like this. If we keep training for a long... We're still not at... Yeah, that's the most important skill, is discipline over time. Let's get helper functions down here. I've got some helper functions that I like to use, and there should be one in here called plot history. What does plot loss curves look like? Okay, so this is, we do actually need a validation data set for this. I don't. Why don't we just write a quick and dirty function to plot the loss curves? We'll reinstantiate the model. Compile it. Stack model. History. And we're going to let's fit for a very decent amount of epochs. 500. See where convergence takes us, because I believe in the paper they did something like 15,000 iterations. Table 18 is where the hyperparameter settings are. Yeah, so for the daily data, which is what we're dealing with, they did 5,000 iterations, so let's do 10% of that, hey? And we'll see where our model starts to converge, or if it starts to converge. So we see, yeah, our MAE starts high and then it'll start bouncing around. And so let's plot model history. History equals history stack model history dot history. Is this where we get it from? I can't remember. Let's have a look at this. Helper functions.py. Yeah, we just need to get the history object from here. We'll just copy this. Except we won't do the val. I wonder where convergence happens. We could random seed this as well, just so we get the same plots every time. Well, the loss is going to be the same curve as the MAE. So we just want to plot the loss over time. No. So it is quite bouncy for the MAE. Samanth, I have an idea for a project that I want to work on. A large scale project that I want to work on going forward. Oh, we're starting to get some loss going towards. Yeah, so the loss looks very bouncy. We'll check it out in a minute. But I have I have an idea of what I want to do for a project going forward. I'll be back in a second. Yeah. Impatient with actions, patient with results. It's a great one. All right, this... So it looks like it converges. But we're still getting fairly bouncy MAEs. And do we have a test data set? A jiu-jitsu stream. I could do that at one of my jiu-jitsu training classes. I'll just use my phone. Let's create a test data set so we can evaluate our model. I'm not stoked at how much how slow my computer is going. Wow, Google Chrome is using Yeah, that's actually quite disgusting what our stack model is performing. 202. So if we're creating a window, wonder how good this model would be if I just predict the next value. So the horizon is only 1. And we'll let it look back. Ten steps at a time. Now that we've got some, let's really clean this up so that we can make our data sets whatever parameters that we want. So let's really make sure that we've got this down pat. So now the look back is 10 and the horizon is 1. So we're just trying to predict the next value. What just happened here? Why was that working? Before. We need self. Now this should work. Okay, so our class was wrong before. Did you pick up on that? We didn't declare the variables here. Yo, Cas9, what's good? You've been using PyTorch for work. How's TensorFlow? I would say they're very similar. I would like to learn more PyTorch as well. That could probably be a future stream. There we go. Okay. YouTube always recommends me my videos. My videos. Man, that YouTube recommendation engine is quite pesky. Let's see if this is modular enough. So right now we're now trying to just predict the next value rather than 14 at a time. Oh, we've hit a fairly low MAE here. But now it's... Yeah, so our loss bounces quite a bit. Let's see where this gets us to though. So now we've got a way to predict on an arbitrary size inputs and outputs. I'm using the latest version of TensorFlow. So 2.5. Okay, we've been standing up for about an hour, so I'm going to sit back down. Wow, the MAE just bounced up to 300. Remember, this is only one data set out of thousands as well. Okay, then we had a pretty good streak of MAE of being 8. But then we see it get quite large here. Cas9 asks, if I'm working on image segmentation, how would you find which data augmentations work best? I'd probably just use rand augment. I'd start with this. If I wanted data augmentation, I'd start with this. Usually because basically, yeah, so versus auto augment, rand augment leads to a 1 to 1.3% improvement over baseline augmentation. This is what I've noticed in all of deep learning in terms of data pre-processing. Usually random beats almost anything. So trust randomness. Okay, maybe this is looking a bit more stable now. Alex, yes, I still sit in the new chair. I'm actually in the market. Oh, here we go. I think we might have reached close to convergence here. So the bouncing region has stopped a lot. Oh no, it's peaked a little. I don't mind that actually. So we get this random outlier loss here. But let's zoom in on this loss function. Yeah, Alex, I was saying I want just a plain wooden chair. Let's make this figure a bit bigger. I think we reach convergence after a fairly long time of training. So if you see here, this starts to get smaller and smaller after a lot of epochs. You said Herman Miller and body chair. What is that? Yeah. That looks like there's too much going on for me. I would want just literally something like this. Wooden chair. This is what I want. that. Why? Because it'll make your body use more of its muscles to actually sit on it. If you have a too comfortable chair, your muscles get too relaxed and too tight. If you have this, they actually have to work to keep you upright. So this is the type of chair I'm after. Just something simple like this. So if anyone makes good chairs, let me know. Okay, so let's zoom in on the epochs. No, we want 300 onwards. Wow. Still incredibly bouncy. Let's reduce this to 400. Now, you got to remember that this is only on one data set. So what are some things to try here? Maybe drop out. How to flatten a loss curve. Yeah, I've gotten to the point where I want things that have stood the test of time. So, wooden chair. I don't care about fancy chairs. I care about simple chairs. That looks cool. Something like that. Or that. That's a nice wooden chair. Look at that. Solid wooden chairs simply offer more quality. Yeah. This is what I want. A nice wooden chair. Yeah. Alex, comfy chairs mess you up. This chair is probably too comfy for me. Simple is best. Yes, you're totally right. Okay, so what are some things that we can try to flatten a loss curve? I like this blog. Hey, Eula. Thank you for the rating. We're talking about wooden chairs and flattening loss curves. Look at this loss curve, disgustingly all over the place. We're replicating a paper, which is NBeats. We've got the model down pat. We just finished building the architecture, which is up here. We've got quite a simple version of it. We've simplified it. We built a block. So this is just the block here. And then we use the functional API of TensorFlow to create a stack. But now we're looking into ways to regularize this training loss curve. There's too many outputs here. See? But let's have a look at how does it go on the test data set. Oh, we get a MAE of 26. But yeah, it's very fluctuating. What did I pronounce wrongly? "23 viewers. Wow, that's a record. I've got the number of viewers hidden because I don't like looking at metrics. Euler. Oh. That's my Australian accent bearing its head. We tend to pronounce everything incorrectly. Okay, Euler. Thank you. Let's compare the predictions to the test. That's actually not too bad. We need to reshape these. How are these going to compare? I would like to build in some prediction intervals for these as well. So let's what function do I have to calculate the results? Simply Samantha says, any plans for image segmentation projects in the future? Who knows? Not at this stage. I don't have any personal problems that are image segmentation at the moment. Where's my helper function for calculating results? Evaluate preds. Oh, very simple. Should have known that. Okay, we have a lot of code here that is very useless, so we're going to have to clean this up. Let's start cleaning this up, right? Stack model results equals evaluate ypred equals, and we have a window size of 10. We'll just set window size equal to window size. Did our stack model beat our original model? Yes, fairly significantly. But is that because it's just an absolute massive amount of layers? So let's compare model 1. Summary. And then, oh, I haven't even defined model 1. Is it just model? Yeah, this is what I mean. This is why we need to clean up some code, because we've been very reckless with how we've developed this model. But let's... Who's got some good techniques? Yeah. So right now, this is our problem. Maybe we need a data set that's larger. Akash, what's going on? Akash says, how to stay updated in AI ML? How much time do you invest in reading research papers? I wouldn't put a number on it, but I would say generally I just read, if something comes out and I'm interested in it, I will read it. So I found this paper and I was interested in it and I decided to read it. I read a great one the other day. Actually, there's a great account on Twitter called AK, which tweets out possibly the best AK. So have a look at this Twitter paper. I mean, account. Here you go. He puts out some, well, I'm not sure who runs the account, but there's a lot of good research papers here. I also write a monthly newsletter called Machine Learning Monthly, but we are getting distracted. There are many different venues. Find your own way to stay updated. My way probably won't suit everyone because it's my way. We need to fix this loss curve. I'm not happy that it's so bouncy. And we also need to... Do we have naive results? Because the naive model is outstandingly good. See, that's the thing with time series data, is that you're going to find it very hard to beat a naive model. So we're going to get out of this. You know what I think we might be able to do is if we insert a dropout layer, let's just find out what happens if we plonk this down here and we re-get it. So while this model is fitting again, I'm going to go back through and tidy up some code. Let's just remember what this looks like, okay, team? Everyone remember what this looks like. Let's see if we can smooth it out using something like dropout. And we're going to chuck in here a val dataset. Validation data equals test dataset. Have we created the test dataset up here? Yes, we have. All right. And so now within our block, this shouldn't be too hard to add in a dropout layer. So maybe I want to drop out what comes out of the stack. Let's just see what happens. Let's just put in a big dropout of 0.5 and just throw it in there and just throw it to the wind. No, we'll pass X through the dropout layer. And let's get a summary of our model. And let's just jump into one of these block layers. We're not going to be able to get it. We're not going to be able to get a layer from there, are we? We'll just trust that it's there. Will this give us a regularization effect? That is the question. We should have really some way to track these much better than what we're doing, but here's the hacker's guide to tracking machine learning experiments. Put them in a comment. So this is without dropout. Oh my goodness. Copied way too much there. I should really write some boilerplate code to set up a weights and biases experiment tracker in Colab so I can just import it. Might be that's a library worth writing. Just add weights and biases to every Colab notebook. Just write a custom callback. That's a good idea. No, that's model 1. See, the beautiful thing about adding dropout here is that we can look into using uncertainty later on. Okay, that'll do for now. And what did we say we're going to do? While this is training, we're going to... So we've added a dropout layer within this block, right at the end. So there's a dropout layer here now. So we're deviating from the paper. What the hell has happened here? Oh. Yeah, so our loss curve is still going like this. Just absolutely dunking on itself. We get these really big losses, like double the loss. Now we'll be able to plot loss curves, actually. Okay. Let's jump through the notebook and start cleaning up some crap. So this is where we set our hyperparameters. This is our time series original predictions. If you see here, yeah, the preds, the naive predictions are very hard to beat. We'll get out of some tabs. We'll get out of an old window. Get rid of this crap. Cas9, what do you usually use for tracking experiments outside of weights and biases? Well, yeah, Alex, you're right. French Toast Mafia. Naive forecasting is actually pretty decent. Well, forecasting is actually BS. So if we just watch this video, if you watch this video, you'll see why forecasting is a load of crap. Well, let's be real. In a closed system, you may be able to get it, but in an open system, forecasting, you run into the turkey problem. Boom. So we could have all of this data, but then there's no way our model's going to be able to incorporate a massive outlier like this. So really what we're doing here with a univariate time series is... Yeah, why is my loss bouncing around like a madman? Wow, then it just blows out of the water down here. This is disgusting. Okay, maybe we're getting some regularization here. No, some convergence. I have looked into Deep Dream from Google. It is very crazy. So dropout looks to be negatively affecting our model's results. Okay, I think we've spent too much time on this. Accuracy. Yeah, see, look at that. What? So they looked at an SMAP over 100,000 data sets of 11.135. Scaled MAPE is not MAPE. Yeah. So dropout negatively affects our model. Does TensorFlow have SMAPE? Symmetric mean. Yeah, the SMAPE algorithm, I mean, loss function, isn't that hard to do. It's just this. But why do they have an epsilon in there? Epsilon. I don't think there is an epsilon in there. What am I missing here? How about we implement a custom loss function? We implement SMAP and see how our model goes compared to the paper. You know what? I actually read somewhere that they don't recommend using the SMAP. So let's get out of this. I want to show you what book was it? I read here. Here we go. SMAP. Hindman and Kohler recommend that the SMAP not be used. It is only included here because it is widely used. So, well, there's the formula for SMAP. Let's just re-implement this just for the hell of it, even though it's recommended it shouldn't be used. Look. They use in the paper SMAP, and that's what they report. But apparently this, whatever this is, thoughts on TensorBoard? I like TensorBoard, but it doesn't, for me, it's not very user friendly. Let's define SMAP. Ypred, we'll go return TF. Well, let's start from the inside. Is that it? Maybe we'll just absolute these as well. Okay. So both of these need to be absolute. Time to stand up. Detox Mango is asking, are data scientists more senior than web devs? Look, that completely depends. I would argue in the beginning of a startup, unless the startup is solely focused on data science, you need people who can build things in the beginning. So a web dev would probably be more important than a data scientist, because unless you have a product that is collecting data, you don't need to run data science on it. So you need a product first before you can run data science. So, okay, let's have a look at, if we just run the results, what are we getting for SMAPE? Well, they just said that they were getting an SMAPE of, this is across 100,000 data sets, mind you. Yeah. SMAPE. So even our crappy predictions are getting a fairly good SMAPE. Yelnats, thank you for the follow. Yelnats reminds me of the book Stanley Yelnats. I think that's a book called Holes. So let's run this one more time. Yeah. I'm not sure why our MAE is bouncing all over the place, but I'll be back. But let's now dig into, before we wrap this up and tie a bow on it, let's now dig into, see if we've missed anything on the training settings. So we're working with the daily data. They use 3 different kinds of losses. They used a look-back window of 10 times the forecast window. they built an ensemble model. We observed on the respective validation sets that for M4 and M3, mixing models trained on a variety of metrics resulted in performance gain. Cass, thank you for the follow. Okay. So it looks like if we keep training for... This is where the MAE is really starting to decrease. But we're still getting that jumping effect. Let's replicate this. An ensemble trained on multiple loss functions. So how could we do that? How do they ensemble it? Ensembling, okay. It's used by all the top entries in the M4 competition. So they found ensembling is a much more powerful regularization technique. So this is C 3.4. Oops. So the addition of these methods improved individual models, but was hurting the performance of the ensemble. The core property of an ensemble is diversity. We build an ensemble using several series of diversity. First, the ensemble models are fit on 3 different metrics: SMAPE, MASE, and MAPE. A version of SMAPE that is only the ground truth value in the denominator. Oh, MAPE. Wait, they use SMAPE, MASE, and MAPE. Let's reload this once again. Mean absolute scaled error. Okay. What's happened here? Did we get an error? We did. In the plot loss. So y true minus y pred over so this takes care of the seasonality. So this is saying TF reduce mean. So this is this part of the equation. But we'd have to be considerate of the shapes of the tensors here. So what is J here? Let's get a ensemble going first to see if it actually improves anything. So their version of MAPE equals How did they combine them? They use 180 total models to report on the test set. Jesus. Okay, this doesn't seem too hard. I'm going to build 3 models first with just simple loss functions that are already in TensorFlow. So I need 3 versions of my stack model. This is where having a model class would be helpful. Ashik, are you talking about Dive into Deep Learning, the book? Let's just make this really simple. Great book. I'm a fan. So I need ways Oh. Okay, so it's saying that we need a get config in our base layer. What if we just went the full hog and trained this for 5,000 epochs like they said? All right, now we should be fish on. Equals, you're kidding me. What typo did we make here? This would be really cool if we could get this ensemble working. Has no attribute theta size. Are you kidding me? Have I got a typo? Oh, I need to recreate my stack model, of course. Boom, baby. Now let's do MSE. And we should be able to get some error bars from this. This will be great if we can. Now we're going to functionize this. We're going to build an ensemble out of this in a second. We're doing it the hacky way first because why not? So when you clone a model using the clone model function, it reinstantiates the model with all of the with randomized weights. Now, do we have... We do. Beautiful. You'll never know when you're ready to start applying for machine learning jobs. I've only ever applied for one machine learning job and I got declined. So just keep coding, keep putting out work, apply for things when you don't think you're ready because you'll never be ready, and start the job before you have it. This article will help you. There's no such thing as being ready, because every unique job will have different requirements, and a lot of them you're going to just learn on the job. So now we want to aggregate the predictions. What do they look like? Okay, so we need to squeeze these. TF. Why did that come out like that? Excuse me? Did Colab lose its brain for a second? I want to look at both of these. Okay, wonderful. So we have 3 different predictions here. This is going to be very, very good. Now, the thing that you're going to notice about these predictions is that they're all slightly different from each other, which is what we want. What has happened here? Oh no. Okay, this is excellent. So, see how each of these predictions are different? This is what we want. So the first one is the MAE preds. They seem pretty terrible. Let's see if this makes sense, if we put these together, and then we can clean it all up later. That's probably actually what we'll do in the next stream, is clean all of this up so that we can make some a legible notebook for people to go through. Okay. And we want all of these in NumPy arrays, or do we? So I need to create a tensor, and I want to take the median across these 3 dimensions. So how could we do that? So if we go TF reduce median, is this an actual method? It doesn't have median? You're kidding me. You're kidding me. There's no TensorFlow median? What am I missing? Is there a TensorFlow median? Does PyTorch have a median? Torch.median. Alright, let's numpyify things. So this is getting the median of all of our predictions to get the... We could do a pretty cool plot as well. Is it just going to get the median value between them? So in this case, it's just always going to pick the MAPE predictions. I'll be back. So we're building an ensemble model here. Let's vertically stack these. Oh, that'd be right in front of the camera. Let's numpy this. Let's I'm going to vertically stack these predictions. And then we'll get the median along the 0th axis. Ensemble preds. Now, we can't compare this to our stacked model because these were only trained on 100 epochs. So let's reevaluate our stacked model just on 100 epochs. Just on one metric, MAE. I now see that this is going to dramatically differ depending on where the stacked model appears. Like what epoch it finishes off. So we should probably have a callback here that saves the best model. Callbacks. Yeah, we want the model checkpoint. That's a delicious loss curve. We ended up with some pretty darn good preds there with our stack model. We even get fairly close to the naive results. Okay, so I think that's good enough for this stream. I'm going to, in the next step, create a callback to save the best model every time. Yeah. So we can see if we can use the functional API to create real stacks. Yes, we can. Does the stack loop create a new block every time it goes through? Yes. The stack model should have n stacks block within it. Yes. So we've done that. We've done that. We've replicated the paper. Next is we want to create ensemble for different loss functions, create callback to save best model weights during training. Loss varies wildly throughout predictions. So, saved best weights and use those. Use callback for ensemble to use 3x best models. And then we want to uncertainty plotting. We also want to use the different loss functions to plot prediction intervals. How does this look? And then we want to apply n beats algorithm to Bitcoin data and compare to LSTMs, deep models, etc. So this was Well, this was today, so this is what we're going to do next. This is what we're doing next. All right? So I need to write in here. Text. To do, create a callback for saving best performing model during training. And then we'll write here. Since the loss varies so much during training, save the best weights and use those. Do the same for the ensemble models. Okay. Beautiful. So, thank you so much for tuning into today's stream. We had a great stream, actually. We got our NBeats block layer working. We implemented that in a functional model. So, this code here, I'm going to delete both of these. This is actually just the entire model, the generic version of the NBeats algorithm. So that's pretty cool, hey? Let's go to figure 1. This here builds stacks of blocks. So over the past few streams, we've created a simple version of the NBeats algorithm here. So we've got, this is the block, so the fully connected layer, and this is the stack. So although the code is very messy, we will move towards cleaning it up in the next stream. We've got some fantastic progress here. The next stage we're going to be doing is replicating the ensembling section. So that's going to be very exciting. We need a way to save our model's best performing results at every epoch. So we'll figure out how to do that. We'll make a callback to do that. But it looks like, yeah, we'll do this. We'll make it fair for our first model to do that too. I'm going to write this here. This should be used for every model. Save the best weights. All right. Will this notebook get uploaded to GitHub? Yes, it will, Ashik, once it's cleaned up. It's still a bit messy. I should really make a Twitch streams folder on GitHub, which just stores all of my Twitch notebooks. But we'll get towards that later. If you want this, you can have it here. If anyone wants the notebook, you can have it here. But it's pretty messy at the moment. So thank you all for tuning in. Hope you had a good time. I'm going for a walk. It's a beautiful sunset. So as always, keep learning, keep moving, and I'll see you next time.